Okay, this is number 3 from the homework, and I'll work through it to kind of demonstrate how to apply the Frobenius method. Number 3 happens to be a case 3. I've already worked through the indicial equation, and the R values are 0 and -1. Remember, in case 3, you prioritize the R's, largest followed by smallest, so this is R1 and that's R2. Our solution we're going to try is y1 equals x to the R1 times the standard summation series, power series about 0, n equals 0 to infinity of a n x to the n. With r being 0, this is just going to be eliminated, so it's the standard power series. That makes y prime equal to the summation n equals 0 to infinity of n a n x to the n minus 1, and y double prime is equal to summation n equals 0 to infinity of n minus 1 times a n x to the n minus 2. Okay, next we're going to basically substitute. So I'm going to put the double prime here, the single prime here, and the original series here, multiply out by their powers of x and 2, and this is what we'll get. The first term is going to be the summation n equals 0 to infinity of n minus 1 times a n x to the n minus 1, because the x will raise the power of the n minus 2 by 1. The middle one is just going to be multiplied by 2, so it's summation n equals 0 to infinity of 2n a n x to the n minus 1. And then finally the last term is going to be x times the original, and that's going to create summation n equals 0 to infinity of a n x to the n plus 1. And then that's all equal to 0. You can see that we have an exponent problem here, which is I can't put these series coefficients together by each power of x unless the powers of x are consistent and generated simultaneously. And this one's 2 powers off from the other one. So because these are both n minus 1s, I'm going to leave them alone. I'm going to change this one. The goal here is to make the n plus 1 into an n minus 1, and all that requires is a shift of index. So I'm going to change the m to an n, and what I want is this. I want the power of n plus 1 to really be equal to m minus 1. And so that's the formula I'll use to make the shift. That means all the n's get replaced by m minus 2. So let's rewrite this with a new index of m minus 2, replacing all the n's. All right, so the first one is summation m minus 2. It goes from 0 to infinity. That's a to the m minus 2, and then that's x to the m plus or minus 1. So that's the same series, it just now uses a new index m instead of n, but because m is equal to n in terms of how it shifted this series, it's basically going to generate the same terms, it just does them with a different index. Okay, well let's rewrite this then in terms of n's so we can put the whole series together. So this is what it'll look like. We'll have summation n equals 0 to infinity. The first term's unchanged, n minus 1, a n x to the n minus 1. Second one's unchanged, summation n equals 0 to infinity of 2n a n x to the n minus 1. And then this one's going to change. This will be plus, and I just want to change the m's back into n. So if m minus 2 goes from 0 to infinity, then n goes from 2 to infinity. So summation n equals 2 to infinity of a to the n minus 2 x to the n minus 1 equals 0. So that change in index has achieved my goal. All 3 of these x's are now going to be in lockstep, which means every index will basically form the same n's. Now I have to fix these indexes a little bit, only because this series doesn't actually generate a term at n equals 0 or 1. So this one starts at 2. There's no problem leaving the 0 there. It's just now I want to start generating terms, and this tells me that this generates nothing until n equals 2. This one doesn't generate terms until n equals 1 because 2n is equal to 0, so I don't want to plug in n equals 0. So now all the series are basically going to generate their first terms at these indexes. It doesn't matter if the series start at the same point, it just matters that they generate terms that have the same powers of x. For instance, there is no n equals 0 terms in this series, but there is an n equals 1. This one generates basically 2 times 1, a1, and that's equal to 0. Because these two series don't generate any terms, this is solely responsible for the only time n equals 1, which means it's the only time that x has a power of 0 on it. Basically, this is the only constant in the entire series. All the rest of them will have powers of x. So this must be 0 because, again, x itself isn't 0, and if that's the only constant on the constant term of x, then it must satisfy the equation. That means all a1s are 0, and I'm actually suspicious if this is a recursive relationship where we skip 2 orders, which is definitely what it looks like, an minus 2 and an, that means probably all the odd powers are going to be 0. Let's check n equals 2 and see what happens with the even ones. When n equals 2, all 3 of these generate terms. So this is going to be 2 times 1 times a2. So it's 2a2. This one's going to be 2 times 2, a2, or 4a2. And this one's going to be a naught. And there's that relationship where we're skipping 2 orders. So that's why I think all of the odd powers are going to be 0. Because of a1, 0, a3 is going to be 0, 5, 7, 9, all the way up. Matter of fact, I can write that down right now. an is equal to 0 when n equals 1, 3, 5, 7, all the way up. Okay, but n2 generates these terms, and that's going to produce this. a2 is going to be negative 1/6 of a naught. And again, being 6, that's one of those factorial numbers. It's not 2 factorial, but it is 3, so I'm suspicious maybe it's n plus 1 factorial. So I'm going to write that down. I'm not sure about it, but maybe the denominator is n plus 1 factorial. Let's check the next one. As I said, I'm going to skip n equals 3 because I'm confident that all of the odds are 0. So n equals 4 is the next one I'm going to check. Well, when n equals 4, this is 4 times 3 or 12 times a4. And this is 2 times 4, 8 times a4 plus 8a4. And then plus a2 is equal to 0. So that means a4 is going to be equal to negative 1/20 of a2. Now, 20 is not a factorial, but it is 5 times 4. And remember, a2 is negative 1/6 of a naught. So I can basically substitute that in and make this 1/120th of a naught. Notice we both had a sign change. And 120, that is 4 plus 1 is 5. That's 5 factorial. So I've verified that the n plus 1 factorial is generating all these denominators. I've also seen that it's simply going to alternate back and forth in sign, and that a naught is going to be part of every term going forward. So I think I can write the nth term now. I think an, and I better do this. I actually want to write it in terms of another variable that's going to generate twice these, because otherwise I'm stuck with this idea that n has to be 2, 4, 6. And what I'd much rather do is have it be an index that starts at 1. So I'm going to call this 2k. 2k then is going to be k equals 1, 2, 3. And 2k is going to generate this. First, it's negative 1 to the k. Because that way when k is 1, it's an odd power, and when k is 2, it's an even power, and it'll change the sign back and forth. A naught's there every time. And then I think the denominator is just n plus 1 factorial. But remember, we're replacing n by 2k, so it's 2k plus 1 factorial. And then every one of these basically generated an x term that was the same as the term we were in. When n was equal to 1, it was x to the first. And when n was equal to 2, it was x to the second. Or, excuse me, there was no x here. This was x to the second. So each one is going to then generate x's to the 2k. So the real solution here, y1, is going to be equal to the summation. I'll just leave k. K equals 1 to infinity. And it's going to be negative 1 to the k A naught's going to be there as part of every term. That's over 2k plus 1 factorial. And then finally, it's going to have x to the 2k. Now, I'm going to do one final step to this one, and this isn't necessary for you to do. It's sort of nice to dress it up a little bit. I'm recognizing that this is almost the Maclaurin series for sine. Sine theta is actually k equals 1 to infinity of negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. So in order to make this perfectly a sine, all I need to do is multiply by an x and then divide by an x. Multiplying by the x creates the 2k plus 1 in the numerator. Dividing by the x, there's no index on this, so that's a constant. It can just come out of the series. So now what I've in essence created, I'm going to pull out a naught and x, is it's a naught over x. And what remains is the Maclaurin series, k equals 1 to infinity of negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial, and that's just sine x. So this thing now turns into a naught sine x over x. And that's y1. That's the first solution to this particular series.